Okay, so in this video I'm going to be cleaning some potassium metal in a very similar way that I cleaned sodium in a previous video. Like sodium, potassium is an alkali metal, and it's quite reactive and it reacts with water and oxygen and other things to get this coating on the outside. This layer on the outside of the potassium is a mixture of various potassium-based oxides as well as potassium hydroxide and potassium carbonate. If we're going to be carrying out a reaction, we want it to be nice shiny potassium metal, and we don't want it to have this other stuff in the mix. The major difference though between potassium and sodium is that potassium is way more reactive. Working with potassium, you have to be much more careful than working with sodium, so the procedure is a little bit different. Like sodium, potassium forms a few different oxides, namely potassium oxide, potassium superoxide, and potassium peroxide. Of all of these oxides, the most dangerous one is the superoxide. The major reason why it's so dangerous is because it's a really strong oxidizer. Generally, if you leave out a piece of potassium and it gets coated with the superoxide, it's not dangerous on its own, and the danger really only arises when you try to cut it. If you try to cut a piece of potassium that's covered in the superoxide, when you cut it with a knife, you'll push a little bit of the superoxide into fresh potassium metal. It reacts with the potassium to form potassium oxide, and this reaction can be so violent that it actually boils the potassium metal. This small amount of boiled potassium metal escapes, and the moment it touches moisture or oxygen in the air, it ignites and reacts explosively. This can have a chain reaction and your entire piece of potassium could light on fire. When I say explosion, it makes it sound like a bomb is going off, but only a very small amount of potassium is vaporized. So there is a violent reaction, but it's small enough that it's not like it's a bomb, and it leads to a very undesirable potassium fire. This is all assuming that you're going to be cutting the potassium dry, but it's often stored in oil, and this actually poses a second problem. If the potassium still has the mineral oil, kerosene, or other organics on it, it can react with the superoxide when it's cut and also ignite it. So you can see why you have to be careful when you're working with old potassium because you really don't want a potassium fire. It's really not that dangerous though to work with old potassium, you just have to not cut it. Make sure you clean it first before you do any cutting. So with that being said, in this video, I'm going to be cleaning some old potassium metal that I left out, not even covered in oil, for about 3 to 4 months. I received it in a bag that was vacuum packed, but obviously there's still going to be some air that gets into there. It was perfectly shiny when I got it, but after a few months of neglect, it was coated with yellow. All of the oxides have the same yellow color, so it's really hard to tell them apart, and I don't really know if it's the peroxide, the superoxide, or just the oxide. Regardless of whether or not I know which oxide it is, I still have to clean it. So I'm going to do this in 2 steps, where the first one is the neutralization of the oxides, and the second one is remelting all the potassium to one glob. I did this in 2 distinct steps because I thought it would be kind of crazy to get liquid potassium mixed with oxides. Anyway, now we will get started with the cleaning. So this is the potassium metal that I neglected and that I'm going to have to clean. Just by looking at it, you can see that all of the pieces are coated with some sort of yellow stuff. Like I said, this is some form of oxide, and whether it's the superoxide or not, we can't be certain. So the first thing I do is I cut open the bag and remove the potassium. I take out all of the pieces of potassium and I place them onto the plastic that they came in. I thought it would be cool to examine and look at the pieces of potassium before I started cleaning them. Just by looking at them, even if you didn't know it was supposed to be shiny, you can tell they're pretty dirty. Luckily, they're not covered with a crazy amount of the oxide, but still they all do have quite a bit of yellow on them. The first thing I do is I fill a beaker with a little bit of toluene. Toluene doesn't react with alkali metals, so it's a good solvent to use when cleaning them. With the toluene added, we can start adding our potassium metal. You can see that when I place it in the flask, there's no reaction that occurs, maybe just a little bit of bubbling as some of the potassium reacts with water that might be in the toluene. You can see here after sitting for a few minutes, it is bubbling due to the presence of water, because it reacts with water to form hydrogen gas. So what I do now is dropwise add 99% isopropanol. It's very important to do the steps slowly because if too much is added, we could potentially start a potassium fire, which would also ignite the toluene. The major reason for using toluene is so that we can have a dilute solution of the isopropyl alcohol. So this process is very slow, and we just dropwise add a couple drops, swirl it around, and let it sit for quite a while. What we're hoping for is that the 99% isopropanol will react with the oxides and destroy them. Oddly enough, I actually couldn't find any literature resources that said anything about reacting the oxides with an alcohol. Maybe I'm just terrible at searching for things, but I honestly couldn't find much of anything. If you have any literature on this, I'd love to see it. Anyway, I'll start with what I know for certain, and then I'll move on to the little more theoretical part. So this 99% isopropanol also has 1% water. It's very well documented that all of these oxides will react with water to form potassium hydroxide, and in the case of the peroxide and superoxide, it will also produce oxygen gas. So letting it sit with this very small amount of water, these oxides can react and they can be destroyed. Now for the more theoretical part, where I kind of assume that it reacts with the alcohol. Like I said, I couldn't find any resources that told me exactly what it formed, but these things are very strong oxidants and they should react with the alcohol. We keep adding more isopropanol, waiting and mixing, and the liquid slowly becomes yellow and dirty. What's nice though is even though the liquid's pretty dirty, you can still see some of the shininess of the potassium coming through. This tells us that the cleaning process is doing something at least. So eventually it becomes time to add fresh toluene to a new beaker and transfer over the potassium. So just using my fingers, I transfer over the potassium to the fresh toluene. What's cool is that you can see that as it's added, the solution kind of takes on a blue color. The solution itself isn't turning blue, but it's actually the blue-purple color of the potassium. When it's just sitting there, you can really see how blue it is. The blue color are oxides that form on the surface, and honestly, I really don't know why it's blue. Anyway, we can add a little bit of isopropanol, and when we mix it up, we can see the blue color disappears. Our goal here is to keep adding isopropanol and waiting until there's no yellow color left. After a while, this solution becomes yellow as well, and if we take out a piece of potassium and hold it in air, a bunch of red stuff appears. You can see that this piece has a lot of red on it, but when it's placed back into the toluene isopropanol mixture, it immediately disappears. I'm not really sure what the red stuff is. I did a little bit of research and didn't find anything conclusive. If you happen to know what this is, I would love to hear it. So now after washing the potassium the second time with toluene, it's pretty clean. Pretty much all of the yellow stuff on the surface is gone, so I feel safe enough to melt it down. To do this, the potassium is transferred to some mineral oil. In theory, the potassium could be melted in the toluene, but I prefer mineral oil because it's less flammable. So to get things started, the heat is turned on and I stir it occasionally. After a while, the oil will heat up and the metal will start to soften even more than it already is. At some point, the potassium will start to melt. Once the first bit of potassium starts to melt, the rest of it should start to melt pretty quickly. After just a few moments, I was left with one large blob of liquid potassium. You can see the irregular shape that it has because not everything is totally melted. You can see here when I'm poking with a spatula that there's still some solid pieces on the inside of the blob. Once everything's totally melted, we're left with a nice blob of potassium. What's cool here is you can see that I can easily stick the spatula right through it. It's still not super shiny though. To remedy this, I put a little bit of isopropyl alcohol into the mix. I don't really recommend adding the isopropanol because you can easily start a potassium fire. Not too long after it's added though, you can see that the potassium is much shinier. One problem though is there's still some stubborn stuff that hasn't been removed floating around on the surface of the potassium. I tried to take them off manually using a spatula, but it really didn't work very well and it was way too difficult. I was only able to get some of it off, so this method isn't the best. I found the best thing to do was to leave it and let it solidify. Once I do this, I can flip it over and we can see that everything's sitting there at the bottom. So while keeping it under the oil, I held the blob in place and I manually scraped off all of the pieces. It didn't really take very long, and eventually the bottom was pretty clean. And now for one final step of cleaning it, we pour some more mineral oil into another beaker. The large potassium blob and as many of the smaller potassium pieces that I could get were also transferred. So just like before, we turn up the heat and we melt the potassium again. This time though, I didn't add any isopropanol because I figured that the amount of oxides on the surface were probably super low. Also, a small amount is bound to form anyway, so there's no real sense in trying to get rid of all of them. So once it's melted, you can see that there are solid oxides on the outside. My hopes in remelting it was that I would get all the small pieces to coalesce together, but unfortunately that was pretty hard to do and it didn't happen. In the end though, that doesn't really matter, and you can see here that besides a thin white film, the potassium's pretty clean. So at this point I was satisfied and I let it cool down back to room temperature. One unfortunate thing when using mineral oil is that the potassium would float in it and a little bit of it is exposed to air. It's not really dangerous, but this part that's exposed might be a little discolored compared to the rest. Anyway, once it's cooled back to room temperature, I add some mineral oil to a container. Then using a spatula, I stab the potassium and I move it over. I push the potassium off using another spatula and I remove everything from the hot plate. Then I close the lid to seal it, and now I have some fresh, clean potassium metal. The one unfortunate thing is that the potassium is floating, and I wished I used a less dense solvent so the potassium would sink. What's interesting is that the toluene washes, when left to stand, jellified. When I chop it up, we can see there's still a lot of liquid content, but there's also a lot of gel. When the other beaker was allowed to stand for a day, the gel totally separated to the bottom and was much more solid. It also took on this very dark red-orange color. And now just for a word about safety and cleanup. I'm demonstrating this to show just how easy it is to start a potassium fire. To neutralize the potassium that's floating around in the mineral oil, you should add isopropyl alcohol slowly in small amounts and let it react over a day. This is just an example of what it might look like if you think that there's just a small amount and it won't really matter if you add some water. So to demonstrate, I pour a bunch of water into the mineral oil. We can stir it around and it doesn't really seem like too much is happening. You'll occasionally get a little bit of flame from potassium when it reacts with the water, but not much. So at this point, you think that it's doing a pretty good job. It seems like the potassium is reacting and nothing dangerous is happening. Well, that's where you'd be wrong, because suddenly, without warning, it bursts into flames. Just after a few moments, you can see we have a nice oil fire going. I transferred the beaker to a pot because I was a little afraid that the heat might break the beaker and splash flaming oil everywhere. Anyway, if this happens, what you should do instead of panicking is simply place something over the top and extinguish it. If it's something like this and easy to contain, you don't need a fire extinguisher, and don't be crazy and shoot water on it and burn your house down. Anyway, that's all I really have to say about cleaning potassium. In the future, I'll probably use it in some syntheses, and I'll also probably get around to eventually making an element series for it. Again, here's a list of the videos that I'm currently editing and future videos I plan to film. In the videos being edited category, you can vote for the one that you want me to publish next, and in the future video category, you can vote for the one that you want me to film next. Also, if you're feeling generous, please donate to my Patreon account because with a bigger budget per video, I can do more things. Also, instead of stockpiling videos, I've decided I'm going to publish them as soon as I edit them, so in the next month or so, there's going to be a lot of videos coming out. On my Patreon, I also added a milestone, and if we get to $250 per video, I'll commit to doing videos for at least 6 months.